2022 A-level Physics MCQ. Question number 39. A uniform magnetic field of flux density B is directed into the plane of paper as shown in the figure. A semicircular conducting loop of radius R rotates at constant angular velocity of omega about O and perpendicular to the plane. The resistance of the loop is 2 ohms. What is the magnitude of the current induced in loop? Consider this loop. This is the diagram, given diagram. When I consider a O radius coming into the flux, and then at that time OB radius goes out from the flux. Therefore, only when generating EMF, one radius only one radius is generating EMF, and EMF is equal rate of change of flux. E equals minus delta phi over delta t. This is rate of change of flux. Rate of change of flux. According to the Faraday and Lenz, this equation gives the EMF, and this minus sign denotes the direction of the EMF. Delta phi over delta t gives the magnitude of the EMF. The rate of change of flux is equal F into B phi R squared. I consider for entire cycle or through one cycle, any of radius, any of these two is in the magnetic field. OA in the magnetic field O, OB also in the magnetic field. When OA comes to the magnetic field, OB is out. But anyway, one radius in the magnetic field. Therefore, we can apply F equals B phi R squared. R is the radius, because this rate of change of magnetic flux is equal phi R squared is the area of the circle, and B phi R squared is the flux through the one circular area, and FB phi R squared is the rate of change of flux. That means within 1 second rotation of the within 1 second the flux change FB phi R squared. Therefore, E equals B phi R squared F. We can apply 2 phi F is equal omega. Omega is given, therefore F is equal omega over 2 phi. E equals omega over 2 phi B phi R squared Therefore, omega phi r squared divided by 2 is the EMF. This EMF acts as a cell through half cycle. The other half, in the other half of the cycle, the other radius generate EMF. Then the direction also change. When we apply Fleming's right hand rule to take the direction of the EMF, I can apply the magnetic flux through the fluxes through the plane. Motion is left side, therefore EMF downside, therefore it has a cell. And when OA comes out, OB goes in the flux, and this is E equals omega phi r squared over 2. Then I can apply V equals IR to the loop. V equals I into 2, I equals B by 2 or E by 2. Instead of V, we can use E. E by 2 is the current through the loop. Therefore, I equals omega phi r squared by 2 into 2. Omega phi r squared by 4. I equals omega phi r squared over 4. B also here. Omega phi r squared B over 4 is the current. Therefore, answer is first one. When we consider the other radius BO comes into the magnetic field, then the EMF, generated EMF downside, that means B to O, in the first occasion the EMF A to O, therefore current also change, the direction of the current also change. Therefore direction of the current change within one half of a cycle. But in this, when generating the current through one half, it's a direct current. Then the change the radius, the direction of the current also change. Answer is number 1.